next guest is Peter. Peter is an assistant professor with the University of Toronto and an affiliate in the Vector Institute for Artificial Intelligence. He obtained his PhD from the National University of Singapore. His research explored the synergies between the artificial intelligence, machine learning, quantum information theory, and quantum computer. As the academic director of the quantum program in the Creative Destruction Lab, he oversees 2,000 quantum software startups a year that exploits contemporary quantum technology in the commercial settings. So we are honored to have Peter tonight.
Thank you. All right. Self-driving cars are a hard problem, but still you have cars that you can put on the road and test them, and you have computers that can learn. Now, when it comes to quantum computers, we have a problem. So if you tell a quantum computer, turn left, and the quantum computer might turn right or might do something completely different. So it's a very early stage technology, and my research focuses on what you use these very early, imperfect, and small-scale quantum computers. So the good news is that you are right in the center of it. So when it comes to building quantum software, and especially quantum applications, Toronto is pretty much #1 in the world. So as far as the U of T goes, we have about a faculty of 10 people who are working on it, which doesn't sound much, but there is something else happening here. We have a startup incubator program where we recruit about 40 people worldwide every year. We bring them to Toronto. We give them a 1-month training in quantum computing, AI, and a couple of technologies that are relevant for them. And we give them some pre-seed money so they can start exploring ideas in quantum computing in a commercial setting. So a couple of application areas are emerging as potential winners for this game. One is logistics, when you have problems related to supply chain, routing vehicles, that sort of stuff. Then we have life sciences and drug discovery. Think about problems related to protein folding or figuring out how enzymes bond, that kind of thing. Then new material discovery is another big area. Here you can think about molecules where it's important what's the quantum mechanical description of that particular compound, how they fold and how they attach to each other. So this is a very natural setting to use a quantum computer for simulating these materials and find new materials. Then the last application area, and this is what every physicist wants to do, is finance, where you have a whole bunch of problems which are a very natural fit for quantum computers, but finance is actually a very hard area to do, because if you don't have data, then there's nothing you can do, whether you're doing classical AI or whether you're doing quantum computing. So that's why we're also talking to RBC, for instance, because they have the data. So we try to get the data, throw a quantum computer at it, and get a startup out of it. Sometimes it works. So we are closing the second cohort, and we just finished recruiting for the third cohort of this incubator program. And this created a huge ecosystem in Toronto. So by now we have the largest number of quantum software startups anywhere in the world. And these startups are dragging in more and more quantum physicists and quantum computing professionals to town. So this is the epicenter of this new emergent field of quantum computing and quantum applications. But let's take a look at the landscape worldwide. So the market is dominated by North American companies. You have the big guys, Microsoft, IBM, Google. They are all building quantum computers, and you have a bunch of startups. Here in town, we have Xanadu. They are building an optical quantum computer. Then you have IonQ in Maryland. D-Wave is the oldest player in this. They are based out of British Columbia. They've been around for 20 years by now. And then 2 years ago, a couple of Chinese companies joined the game. And if you look at, say, some figures of how much investment went into it. So D-Wave is the oldest player. They raised about $200 million over the 20-year history. They are still not profitable, but they are getting there. And it got really interesting 2 years ago when Alibaba announced that they are committing $15 billion to build a quantum computer. that was a signal. So immediately the US federal government said that we have to do something about it. So they committed about $1.3 billion to building quantum computers, and most of it actually went to IBM. And if you look at these different initiatives, some of these quantum computers are actually accessible for free today through a Python API, so you can actually start using them. D-Wave offers cloud services. I think they give you 3 seconds a month for free, which that doesn't sound like a lot, but if you consider that one calculation, one round on the chip to pull out 1,000 samples is 10 milliseconds, that means that you can run 300 jobs. It's not too bad. And Rigetti also has a free offering. IBM had a free offering for 2 years by now. Google will launch its quantum cloud service early next year. And Alibaba sometimes offers a free access, but sometimes they just shut it down. They have an 11 qubit quantum computer. So these are things that you can access today. And so a big question is then, like, why should we care about quantum-enhanced machine learning? Like, why is this a good application area for these imperfect quantum devices? Well, there are many arguments for this. But let's approach from the classical machine learning angle. So when you think about the state of the art in machine learning today, you are already using a variety of different hardware backends. 10 years ago, you only used CPUs. And when you use a CPU for a learning algorithm, what you're doing is that you take that algorithm and you decompose it into elementary operations, just additions and multiplications. And you must do this decomposition. So eventually, you execute your program on the 64-bit registers of a CPU. And you do pretty much the same on the GPU, except in parallel. And instead of 64-bit operations, you typically use 32-bit operations, but it's the same idea. You're decomposing the problem, and you have this massive parallelism, so you just execute the same operation on 5,000 cores, or depends on how many GPUs you can throw at the problem. But the problem with GPUs is that they use a lot of power. So now you have these other architectures like field programmable gate arrays and all sorts of application-specific integrated circuits to do these parallel operations, but at a much lower power cost. So if you look at, for instance, the tensor processing units that Google produces, those have a fraction of the power use of GPUs, but they can perform almost at the same throughput when it comes to like numerical number crunching. What's common to all of these is that they're all digital. They're just the same classical digital architecture, which means that a calculation is always deterministic. So if you add 2 numbers, it always adds up to the same number. And in principle, these operations are parallelizable in the sense that you decompose the operations, and in many, many cases, you just run the same operation simultaneously in multiple cores. Now, let's add quantum devices to this mix. So quantum devices are not deterministic. Every quantum calculation is quintessentially probabilistic. This is a big difference. Have we ever heard that a qubit is both 0 and 1 at the same time? It's a lie. What it is, it's a probability distribution between 0 and 1. It's just like coin flipping. You flip a coin, and every time it lands on your hand, it's either heads or tails. But you don't say, when it's in the air that, hey, it's both heads and tails at the same time. So it doesn't make much sense. And it's the same story with a qubit. It's just a probability distribution between 0 and 1. And what a quantum calculation is, it's just a transformation between probability distributions. So you start with some distribution and you transform it into another one. That's what quantum computation is about. But it is quintessentially probabilistic. And the second big difference is that you don't want to decompose operations. You want to execute programs, and you want to solve problems which cannot be decomposed the same way you decompose operations for a digital computer. So if your calculation is global on some structure, that's a good fit for a quantum computer. So these are the 2 big differences: probabilistic calculations and global calculations. And when you think about what you can do with these digital architectures, you know very well that they excel at supervised learning tasks. So when there's something to imitate, like you saw in the previous talk, and it's also very, very good at discriminating between things. The easiest thing is to discriminate between cats and dogs and images. But when it comes to machine translation, you are also essentially discriminating, because you are taking a sentence and you're generating a new sentence. But when you're generating this new sentence, when it comes to picking the next word, you're essentially discriminating between, say, 20,000 possible next words. So it sounds like a generative problem, but it's actually a discriminative problem. And my pitch for quantum machine learning is that you shouldn't solve problems with quantum computers that you can solve with a GPU cluster, because you can buy a decent GPU cluster for $100,000, $200,000. So why would you use a $10 million quantum computer to solve the same thing? So I think the interesting question to ask is, like, what are the hard problems in AI today, and whether we can address those by using quantum resources. So this is why I focus on mainly unsupervised learning problems and generative learning problems, which remain hard. Sure, there are advances, and there are many sub-problems that you can solve with just deep learning alone. But many, 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 many questions remain open, and I think this is where quantum devices can give you an advantage. All right. To make things more confusing, when we talk about quantum computing, we are talking about several different things. The Holy Grail is what you see on the left. This is called a gate model quantum computer. This is universal in a very well-defined sense. So when you think about a digital computer, so let's go back to this 64-bit register. This 64 bits is just a string of zeros and ones. And you know that you can transform this string of zeros and ones into any other string of zeros and ones. That's what digital computing is about. So since you can arrive from any bit string to any other bit string, it's universal. And you can do it with just two operations, a NOT gate and an AND gate. And that's all you need. This is what the gate model quantum computer can do for you. But the universally applies to these transformations between probability distributions. So this means that you can start with any quantum probability distribution and transform it to any other quantum probability distribution. And the surprising fact, and this is a result from the 1990s, that you also need just a finite set of gates. So for a classical computer, you only need 2 gates. For a quantum computer, you need 3 gates. And you can make that universal. But it's notoriously hard to build. We still don't have a system that's beyond 79 qubits. On the other hand, there's something different that we can build today at a fairly large scale. This is called a quantum annealer. So this is not universal. You can't just map any distribution to any other distribution. It solves one problem. It solves an optimization problem. It's a discrete optimization problem. So say you have discrete random variables and you want to find some optimum of the combination of these variables. That's what it is useful for. So the big advantage of this is that we are up to 2,000 qubits today in a superconducting architecture. And the 5,000 qubit version is being benchmarked right now, and it will be commercially available a year from now. So this is a lot more scalable, a lot easier to build. And I don't have a slide on this, but to make things even more confusing than this, nobody agrees on what's the best technology to build quantum computers. So you can use, for instance, the exact same silicon-based technology that you have in every digital device that you own. The only difference is that you cool them down to near absolute zero, to about 10 millikelvin. These are called superconducting architectures. So the quantum annealer is built with this. Google, Microsoft, Rigetti, Alibaba are all building this superconducting-based quantum computer. There are problems because this is a 2-dimensional surface, so it will have some limitations on what kind of calculations you can perform. So it's a little bit less universal than we want it to be, but this is the easiest to fabricate. That's why the competition is the heaviest in this area. But there are also other architectures, and we just don't know which one is going to win. So as I mentioned, there is a quantum computer being built in Toronto that's an optical system. That doesn't have to be cooled down. It operates at room temperature, but it's a slightly different way of thinking because you are working with light, and light doesn't like to stay in place. So your photons, the particles of light just keep moving around instead of being in place. So it's a little bit different of how you construct this quantum computer. Then you have trapped ions. In trapped ions, you do something really cool. So you have some substrate that can emit individual atoms, and you trap these individual atoms in between laser beams. And so these atoms are floating above the substrate in a series of laser traps, and then you interact the atoms in a particular way to perform calculations. So this is the largest universal quantum computer today. They have 79 qubits in a single trap. So we don't know which one is going to give us millions of qubits, but the truth is that we need millions of qubits, and we only have 79. So we are very, very, very far from where we want to be in terms of scale. And there's another additional problem. So it's not just scale that matters. It's not just the qubit numbers that matter. So this is our quantum processor as we want it to be, isolated from everything, floating in some vacuum. But that's not what happens. This quantum processor interacts with the environment in an obnoxious way. We don't know exactly how to control this interaction with the environment. But this interaction is something that keeps destroying the calculations we want to perform. And this puts a limit on how long the quantum code can be that we put on the quantum processor. So think about it this way. Think about it as you are building some deep learning network. You are used to having, say, 15,000 lines of code. You can put as many convolutional layers, pooling layers, and whatnot, and you end up with 15,000 lines of Python code. But you can't do that on a quantum computer because you are limited to 12 lines of code. After that, your calculation no longer resembles what you want it to be because of this interaction with the environment. So for the next 5 and possibly next 10 years, we are going to live in this hybrid classical quantum paradigm where we do a short burst of calculation on a quantum processor, extract those results, process them on a classical computer, then go back and run a short burst of calculation on a quantum computer again, and iteratively do this. So today we can execute quantum programs of maybe 12 gates, so think of 10 lines of code. By the end of the year, we will be up to 20. And hopefully in a couple of years, we can execute a few hundred lines of code, and that will help us create more meaningful applications. Talking about applications, I'm going to give you 3 examples where you can use quantum computers today, where we expect some kind of a supremacy result soon enough. But before I dive into it, I want to talk a little bit about this quantum supremacy. So with these noisy, small-scale devices, you just cannot expect this exponential speed up that the media sometimes claims. It's just not true. And I'm very fed up with this claim. So a year ago, I published a paper just proving how bad the situation is. I took one of these algorithms that promises an exponential speed up, and I implemented it on 2 quantum computers, on an 8-qubit Rigetti device and on the IBM quantum device, a 16-qubit device. And after running the algorithm many, many, many times, for instance, on the Rigetti device, it was so bad that I got exactly 0% overlap at the end of the calculation with the correct result. And I was implementing a toy problem. I was trying to invert a 2-by-2 matrix. So that's your exponential advantage today. You can forget that. So the quantum supremacy game today is about showing some constant time speed up. Say if you can do something 2 times faster, that's good enough. If you can do something 7 times faster, that's fantastic. And that might not sound compelling, but when you think about GPUs, that's exactly the advantage they offer over CPUs. So that's why I think about quantum computers as just another accelerator that you can add to your existing stack of different devices that you use for machine learning. So there are some calculations that you can accelerate on it, just the same way as you accelerate some calculations on a GPU. And optimization, discrete optimization, is one of these examples. It doesn't matter what kind of quantum computer you have. I mentioned quantum annealers, I mentioned gate model quantum computers. I didn't talk about coherentizing machines, but there's a variety of quantum hardware out there that you can use, and they can all do optimization. It's a very natural fit for quantum computers. So just to give you a rough idea of how it works, is that imagine that you have a uniform distribution over all possible solutions. Okay? In quantum physics terminology, this means that you have a complete superposition. And starting from there, what you are doing is that you are doing this quantum calculation, this transformation of probability distribution in such a way that it peaks over the optimal solution. And then you sample that. So you keep sampling a few times, maybe 1,000 times, and say half of those samples will give you the optimum. And then you just accept that, hey, I found the optimum. And then you can ask, what is it that I can do with discrete optimization in machine learning? Well, you most definitely shouldn't do deep learning. Because when you think about deep learning, you typically have 32-bit weights on every single connection, and you have a few billion of these connections. Now, the largest quantum computer we have today is a quantum annealer, and it has 2,000 qubits. So you cannot meaningfully embed the problem on a quantum computer. And I mentioned that a calculation on a quantum computer is always global. So it's not like, you have your 64-bit registers or 32-bit registers, and you decompose the problem into small pieces. No. You have to embed the whole thing at the same time, otherwise it's just not interesting for quantum computing. Then you can do it classically. That's a big difference. So you'd better, if you have 2,000 qubits, then you better use all of them. And it should express your entire problem. So you cannot do deep learning on a quantum computer. Not yet. Maybe in 45 years, but not today. So what else can you do? But there are problems in machine learning which are quintessentially discrete. Like if you ever tried a Kaggle competition, you probably figured out that the winning entries are always some kind of an ensemble of different learning models. The components can be deep learning models that you train separately, but combining them into a single predictor that's stronger than every individual component is a discrete optimization problem. That's a good fit for quantum computing. And one of the earliest demonstrations, which was in 2008, happened with this kind of mindset. And then 2 years ago, they used the same approach to rediscover the Higgs boson. It was more of a tour de force than anything else. And you can start thinking about problems in meta learning, where you also have a bunch of discrete optimization problems. So these map very well to these quantum optimizers. Then the next big area is different types of unsupervised learning. So if you can map your unsupervised learning problem to a graph, then you can come up with various optimization schemes over this graph that identify the structure that you are interested in. So think about identifying dense subgraphs, or think about clustering, where let's say a max cut would identify the two clusters in your data set. These all map to these graph problems, and you can solve them with quantum computers. The next big area is sampling. So every single quantum calculation is probabilistic, which means that you can sample probability distributions for cheap. Now, I also told you that we have this problem that your quantum processor interacts with the environment. But you don't have to regard this as an enemy, because it turns out if you just let this interaction happen, then your quantum system will equilibrate with the environment. This is the very same thing what happens when you have a cup of coffee and you don't have the lid on. Then your cup of coffee is going to equilibrate with the environment, which is the room, and it will reach the temperature of the room. It's the exact same process happening at the level of the quantum device. So noise is not necessarily an enemy. You can use it for calculation, because equilibration is something very expensive to calculate on a digital computer. So you equilibrate, which in physics terms means that you reach the thermal state of your quantum system. And in machine learning terminology, this means that you can sample a Boltzmann distribution for cheap. And the Boltzmann distribution is actually very difficult to simulate and sample classically. In fact, it's Sharpie complete. So you have this entire family of machine learning models, probabilistic graphical models, that people don't use because they are just mighty expensive to train and then to use for inference. Like once you train a deep learning network, you can load it on a phone and just deploy it there and use it. But with these models, inference itself is still Sharpie complete. It remains notoriously difficult. But they can do things that deep learning cannot. Like you can ask probabilistic queries. Say a patient walks into the doctor with a bunch of symptoms. You can ask what's the most likely disease. And if that's the most likely disease, what are the other symptoms that we should check that the person has? So these probabilistic queries cannot be asked from a deep learning model. So this complements those models. And you can use a quantum computer to train them and to do inference over them. So I think this is huge. Some of my own research also focuses on this. So I'm interested in combining this approach of probabilistic graphical models with this like old school AI where you have logical propositions. And it turns out that it's a good fit. It's a very good fit for quantum computers for a variety of reasons. But there's a lot more to it. So one of the many problems that we have when it comes to building software over quantum computers is that there is no abstraction. So if when you're computing with a quantum computer, you have to program them at the level of gates. This means that in classical computing terms, this would be assembly. Now raise your hand if you can program in assembly. Okay, I see 5 hands, maybe 6, right? And I'm sure that the entire room would raise their hand if I asked about Python. So there's no Python for expressing quantum programs. So I told you that you access these quantum computers through a Python API, but the instructions that you give to the quantum computers are gate level, are assembly level, and there is just no abstraction. And one possible way of creating this missing abstraction layer is by accepting and embracing this probabilistic layer nature and then look at probabilistic programming. So there is this very nice project called Curry. I think since then they changed the C to Q. So this builds a probabilistic programming abstraction for quantum computers. And I was kind of approaching from the other direction with this paper. So I was using probabilistic programming for studying physics, but you can actually merge the two and have this very nice expressive way of dealing with quantum computers, whether it's for machine learning or for solving quantum physics problems. So that was the second primitive. So we had the first one was optimization, second was sampling, and the third one is evaluating kernels. So this is really cool. So quantum computers very naturally give rise to some really weird functions. So you can start thinking about using these functions in, say, constructing different quantum neural networks. And until a year ago, any paper that mentioned quantum neural network was written by crackpots with probability 1. So it was just a very bad area because people think about like quantum effects in the brain and all that sort of stuff that's completely unsubstantiated. And finally it changed last year, as you can see from the dates on arXiv, right? That was last March, last April. Finally, people figured out how to build meaningful quantum neural networks. And then there was another result in November last year, which is really cool. It turns out that if you have some quantum component in a larger neural network, then you can backpropagate the whole thing. So you can have convolutional layers, pooling layers, fully connected layers, a quantum layer, another fully connected layer, and you can just backpropagate the whole thing. So you can create these really cool hybrid architectures where you can have like classical and quantum components all over the place. So this is a very, very general computational model. Neural networks themselves are universal function approximators. Now throw some quantum stuff at it, and you have something really interesting coming out of it. So now we have this computational model since last November, and now we are looking for a problem where we can get some benefit with it, right? So we can run simulations, or we can use actual quantum computers, and we are looking for a problem where this architecture will give you an advantage over, say, some deep convolutional neural network. So in summary, you are at the very center of what's happening in quantum software development and quantum machine learning. If you want to learn more, sign up for my MOOC. It restarted a week and a half ago. So far, we have 5,000 students. It's really fun. The prerequisite for this is linear algebra. That's pretty much the language of quantum computing. So if your linear algebra is strong, then feel compelled to sign up for this course. And my key takeaways are that quantum computers are here. They are really, really imperfect. You have to be very careful of how you phrase a problem and how you deal with noise and the scale and all of those. But you can start programming them. And really, this is the best place in the world if you want to get started with QML. Thank you.
Hi everyone, my name is Devang Swami, and very fascinating talk and very inspiring one. My question is more in the sense with when you said using assembly language. So I wanted to know what is the instructor set architecture, ISA, that is being used. Like in normal CPUs, I know RISC is one of the open source ones that we are using. Then AMD and Intel have their own instruction set architecture. So is there an open source instruction set architecture with the quantum computers?
There are at least 3 of them. It's very annoying. In fact, by now we are getting to the stage that you get these transpilers that can translate between the different sets of open source instructions. So yes, and as I said, you only need 3 gates to be universal, but all of these frameworks offer you 20 different gates. And the tricky part is that, so you express your problem in the language of these 20 different gates that a particular framework offers, but the hardware only implements the 3. And then there is an additional layer of compilation, how you decompose these 20 gates that you expressed in your program to the quantum computer. And this problem in itself is at least, I don't know, it's definitely NP hard. But it can be done. There are open source frameworks, but quantum compilation itself is a huge research field with plenty of open problems. So if you are into designing languages and into compilation, just jump into quantum computing right now.
Hey, so you mentioned that most of the providers today of quantum computing architecture is offering it over cloud services. My question is as follows. I imagine any problem that you would solve on using a quantum algorithm could be simulated using classical computers?
Or as of today, 29th of May, 2019, yes, you can simulate everything that the chips offer you to do. This might change by the fall.
Yeah, so I was setting it up.
So yeah, but anyway, the short answer is that yes, you can simulate everything. It might take a fair bit of resources. So for D-Wave, you probably need a GPU cluster for the more intricate calculations. For like these 16-qubit or 20-qubit devices, you can simulate it on your phone. Yeah.
So what I was setting up here is that, is there a problem that you can throw at a quantum computer to actually mathematically prove that you're actually getting a quantum computer on the other side of the cloud, and not just somebody who's simulating it, claiming that they're getting, and then just putting a lot of power into it at a loss perhaps, but just to generate fundraising?
We have to have a discussion, but let me give you a short answer to this. So this is the question that everybody asks who is serious about verifying quantum computers. And so for instance, IBM has been running this service for 2 years. And they say that, yes, your programs run on the quantum computer. But since it's very easy to simulate everything at the level of 16 qubits, including noise, imperfections, everything, we don't know. And they don't give you access to the low-level compilation and everything to verify that. So there is a very exciting initiative in IQC in Waterloo. They are building a fully open source quantum computer where you can access everything from the hardware design to the control of the quantum computer, to the software stack and everything. So this is for researchers exactly for this, to have verifiably quantum calculations. So it's in the making. And once we have larger quantum computers, I would say above 100 qubits, then those are very, very, very difficult to simulate. So the state-of-the-art simulation is 70 qubits. That's the largest quantum system that was ever simulated. But those are perfect qubits. With these noisy qubits, you can scale further. Oh, but, okay, then let me say just one more thing. Like, I'm personally very upset about this issue. So we created a foundation. It's based in Toronto. It's called Quantum Open Source Foundation. And one of the things that we do is we are creating benchmarks, and we are trying to force the vendors themselves to open up more so we can run these benchmarks closer and closer to the hardware to make them comparable. Because every single quantum computing vendor comes up with its own metrics that say that, hey, my quantum computer is the best. Look at our figures. And you know, it's just not scientific.
Oh. Hey, sorry. Yeah, so great talk. Just as a student who's very interested in quantum computing, not from a technical standpoint, but actually from an application-based standpoint, what do you think is the best way for someone like myself to like kind of prepare for what the industry is going to provide, and like how do I get on it to start creating applications for this device as soon as possible? Because right now you guys are still so exploratory. Like obviously I want to understand like half the slides you said in the slides, but like I don't come from a physics background, but like the potential possibilities with the technologies would be unreal. So like what would you recommend for someone who's looking at this from like a business case perspective? Like what can I create with this? What kind of simulations can I provide that's going to create value? Like how do you recommend someone for me to like prepare for like the day we reach to singularity?
So this is a very important question, and this is the question that many people ask, because it's difficult to train a quantum physicist in quantum computing. It's even harder to train a computer scientist in quantum computing. And when it comes to, say, an MBA student, it's infinitely hard. But this is I tried. But this problem has to be solved. And we have a startup incubator in town. Like every year we run a 1-month boot camp training physicists, computer scientists, and MBA students in quantum computing and how to build quantum applications. So we have varying levels of success. We actually succeeded with some MBA students. And so I'm worried about this problem. But I also see that this is an opportunity. So we have lots of initiatives in the University of Toronto to create education at various levels, master's, PhD, and postdoc, and also to spread out, like branch out beyond physics and computer science. So for instance, in the Rotman School of Management, we are creating a course which is called Commercialization of Quantum Technologies, which would address sort of the question that you are asking. If you have a less technical background, like what do you do? Then so that course would address this. But that's an undergraduate level course, which takes about 1.5 years to approve. So you can look forward to that course in like September 2020. But I'm working on it. Right now, take a look at the MOOC. If it's above your level, then just look at the list of references in the syllabus, and you might find something that's at your level that can get you started.
Okay, thank you very much.
Thank you.
Peter.